Having seen on the first tutorial how to get familiar with the GNU Radio Companion interface and how we can interact with generated Python graph using the Python snippet, and during the second tutorial how to interact with the IQ stream with a dedicated Python block, let's just see as a final presentation how to interact with external tools, because GNU Radio might not be the best suited processing framework for finalizing your processing. GNU Radio is very efficient in processing the streams, continuous data, but maybe at the end you want to analyze packets, you want to do a correlation, or you might want to do operations that are not best suited for GNU Radio. So the first approach that we will not develop is using name pipes. We've seen at the end of a previous tutorial how we can use a file source for feeding a flowchart. And if you use a FIFO, first in, first out, name pipe under Unix, mkFIFO, then you can actually replace the name of a file with one of these FIFO. More interestingly, we're going to stream data through ZMQ, which relies on TCP/IP, so trying to stream data over an internet compatible network, and this will allow us to stream continuously data even if no one is listening, such as in a UDP connection. But this will also allow us to address how to change the flowchart parameters using RPC. We're going to conclude with correlation because you will not find a correlator block in GNU Radio, and we'll see how we can actually use signal processing for performing the correlation. So the context in which we're using, for example, ZMQ is the example here of a ground synthetic aperture radar, GBSAR, where a bistatic radar with a transmitter and a receiver are connected to an 83 Research B210 software-defined radio, whose data are collected by the Raspberry Pi here. Now, in a synthetic aperture radar, range is provided by the bandwidth of a signal being broadcast by radar, but azimuth, meaning the direction of arrival, is provided by the spatial diversity of moving the antenna here along this rail. In this example, we wish to move the whole setup, including transmitter, receiver, SDR platform, and Raspberry Pi, along with the antennas, but only collect data as they are fixed in a location where the antenna position is stable. The control of the antenna is under supervision of a Raspberry Pi, which receives order from the PC collecting the data. So the PC is continuously receiving data, only stores them if the antenna are at a known stable location, sends a command to the Raspberry Pi to move by one step, waits until the antenna are at a fixed location, and then collects the new data. In any case, the SDR stream must never stop, otherwise the phase condition between transmitter and receiver might be lost, so we never want to miss a single sample, continuously recording and streaming, and yet we need to only collect the data when the antenna are stable. To give you an example of a result, here is the antenna location. We've got 4 targets, here a container, here a building, and actually, funnily enough, this building, which is detected at this location, was built before this Google map image was updated. And we have one final faraway target behind the trees here, which are transparent to microwaves. So how do we actually use at best the various capabilities of GNU Radio to stream the data, in this case to an Octave or Python script, performing the data collection, cross-correlation, and analysis of information collected by the radar? To illustrate this, we start with a new flowchart, and as again, we start with a signal source which will generate the data, because again, we're not going to have any hardware limiting clock. We put a throttle block, but this time, in addition to displaying the time domain oscilloscope output, we wish to stream the data. So at this point, we can save as this guy as the transmitter of data, and as we've seen earlier, if we just run this guy, we get an oscilloscope output with I and Q coefficients. Now, this, we do not want to collect the data on the same computer, but we want to share them with another computer. So we can call the ZMQ. ZMQ is a set of libraries above TCP/IP. And the beauty of ZMQ is that it will guarantee the consistency of a broadcast information. So you don't have at the application level to reassemble the structures that you transmit. ZMQ will make sure that whatever you're transmitting is received on the other end. We have two sets, the publish subscribe, pub sub. The publish subscribe framework is a UDP-like, meaning that if someone is listening to the published data, they will be received. If no one is listening, too bad, they're lost. And that's exactly what we want for the radar application, whereas the antennas are moving, we don't want to record the data, but we don't want the SDR to stop collecting information. And the TCP-like, so connected mode, is the reply request, reprec, where in this case a client will ask a server for some data, and the exchange is guaranteed to be consistent. So in this case of a publish subscribe, the only parameter we need to provide is the address, which is a URL with TCP something. In this case, we're going to send to the same computer, so ourselves is 127.0.0.1 or hello, and we need to select a port number, which is a port bigger than 1024 and smaller than 65,000. So let's take a random port. The first thing is, if we run this flowchart, as you've seen that we have not put any receiver, yet the data are continuously updated and collected. So meaning that this part of the block is continuously running, even though there is no one connected to the sink on this side. We might make this a bit more interactive by setting the frequency as a range. And as we've done now multiple times, we select this as a range. We know that the maximum value is semperate over 2. The minimum value is minus, but we don't care about this. We're going to put something a bit bigger here. And this is the frequency that we set on this flowchart. So again, we can demonstrate that this flowchart is actually running even though we are not streaming data, because the frequency indeed changes when we interact, even though no one is listening to the publish. So now if we create a new Qt interface, but this one is using a ZMQ sync, so this one, it will be a publish subscribe to subscribe source. We need to put the same URL as before, so meaning that we collect data on the local host on the same port as we did earlier. And this time we will not put any throttle block because the data are already throttled. So even though this flowchart will warn us that there is no rate limiting block, we know that on the output we are going to limit the data rate with the outgoing stream rate. So in this case, again, we can display what has been received. Now this is going to run in the same GNU Radio Companion framework, but of course this could be running on two different computers. If we now run this guy over here, nothing is going to happen. GNU Radio Companion warns us that there is no throttle bot, but we know that this is a valid flowchart. And if we now run on this guy over here, the outcome of this flowchart here, we see that the receiver is indeed receiving the data, and as we're changing the transmitter, the receiver is changing accordingly. So this demonstrates how we can stream data from GNU Radio to external software. And the beauty of ZMQ is that it's available to so many other frameworks. If we just quickly look on the slides, we've got ZMQ for Python. So if you don't want to rely on your remote processing server with a GNU Radio block, but with only Python, you can instantiate a ZMQ socket with a subscribe. Here we change port, but it's the same story on the local host. And we interpret the array. In this case, it's integers because we did a conversion from floating point to integers. So if you had received data which are floating point 32, you would put an F. So you convert the array of bytes into the right data that you transmitted through the ZMQ publish subscribe. Similarly, you could do the same with Octave. Octave is provided with the ZMQ package. And in this case, you would ZMQ subscribe a socket, you would connect to the same local host, and you receive an array of bytes which you convert, typecast, in this example, an integer 32, or to a single float, single complex, depending on the data that you've transmitted. So you see that in this case, GNU Radio can very efficiently interact with Octave or Python or C language. In the C language, you've got the ZMQ socket and the same story. So this allows us to efficiently stream data from GNU Radio to external tools. However, at the moment we're cheating because you see that this frequency is changed from the data source, whereas we wanted to be able to move the antenna from the data, from the software collecting the data. So in this case, these are the stream of IQ coefficients received by the control software, and this is the software that should be controlling the antenna position, or in this example the frequency, not the other way around. So in order to be able to change the parameter frequency here, we would like to send a command from the receiver to the transmitter. And we could, of course, as we've seen earlier, create a TCP/IP server in a different thread. And since the TCP/IP server has access to the setter and getter, it could change the frequency variable which has been associated with a setter. However, a more elegant solution, which does not require developing a whole client server, is sharing the information as an XML information, so a format that is easily readable by a computer. And in this case, we could have a server that waits to receive commands and can change by calling a callback function associated with a remote process control, RPC. In order to do this, all we need to do is launch an XMLRPC server. In this case, it's connected to port 8080. And on the opposite side, we need to put an RPC client. So the RPC client over here is connected to the same port so that the client and the server are talking on the same port. And we need to call a callback function. So here the value variable is a frequency, so we need to call the callback function setFrec. And we need to trigger the callback function when a local variable is changed. Let's say my frequency, my frec. And this my frec will be changed by a range. So this time we create a slider which is associated with a my frec value, which we know to be going from 0 to semperate over 2, and we can set its initial value to a different quantity here. So this time we have a local variable that will create a callback function associated with XMLRPC client. The callback function will be triggered whenever the slider is changing myFrec function. This myFrec function will be provided an argument to setFrec, and setFrec here is the same variable name as the frec that we've selected over here. So the string is important because it's the same variable name that is used in the callback function over here. So now if we run this flowchart, it starts with a default value of 1000 Hertz. And now if we run this guy over here and go back to this, you see that we display the same value, but this time if the client is changing the frequency, then the server is changing accordingly. So this means that now using the XML, and actually we can be convinced because we're going to get some messages on the console from the XML display that some messages has been received and that we have indeed acknowledged the new value that have been transmitted by the client. Also notice that as before, if we run the transmitter and the receiver both sharing data through ZMQ and XMLRPC, then we can actually, so this is the transmitter and the receiver is going to come here. We can actually, so not only change using the client and server, but we can actually send commands through the XMLRPC shell command, saying that we want to send on the port at which the XMLRPC server is running. We call the callback function and we say we want to send an integer with a given value. And indeed we see that both flowcharts are changing when we broadcast the value from the shell. So this concludes this set of tutorial about GNU Radio Companion and how to interact between GNU Radio and external software for distributed processing. So the last thing now is we are able to record data on a remote processor that is collecting a continuous stream but only recording when the antenna is in a static position, and we wish to know the range to the various targets. How do we calculate a range? A range is calculated by trying to search for a known transmitted pattern, and in our case we are recording the information that is being broadcast to illuminate the scene with noisy received data. In order to identify the time of flight of the signal to reach the target and being backscattered, we need to cross-correlate. Cross-correlate means we multiply the received signal with a known pattern shifted by a time tau, which is varying along the cross-correlation. Now these two quantities are assumed to be mean value 0, so that when the pattern is not found in the signal, this multiplication will be randomly positive or negative, and the mean value when integrating the energy will be 0, except if the pattern is found on the signal, then the multiplication of positive times positive is positive, or negative times negative is positive, and energy will accumulate coherently. So by using the cross-correlation, we can try and identify the range of a target. Now, if we search in the GNU Radio blocks, we will find a header correlate where we can have a digital header and try to find for the synchronization word in the received bit stream, but there is no cross-correlation, meaning an array of complex or real numbers that we wish to correlate with the received signal. So how are we going to do this? In order to implement the correlation in GNU Radio, we need to remember that there is a close relationship between convolution and correlation. Convolution is integral of a signal times the received pattern tau minus t, and we've seen just earlier that the correlation is the same quantity but with tau plus t. So the only difference between the two is that in this case the time is running negatively in the argument of the integral, and here it's running positively. So we need to flip the time, and in order to flip the time, we have a complex conjugate of the argument, because exponential of j omega t complex conjugate is exponential of minus j omega t. And because we know from the convolution theorem that the convolution of two quantities is the Fourier transform, is the inverse Fourier transform of a product of a Fourier transform, then the Fourier transform of a correlation is the product of a Fourier transform complex conjugate. That's the important aspect, is that now we have a complex conjugate to subtract the phases rather than add them. So how do we actually run a correlation in GNU Radio? So starting again with a blank flowchart, we can try to make a noise radar by saying we have a known transmitted pattern, and again the known is very important. In a radar it's called the reference channel, and this reference channel will be throttled because again we have no real hardware, but most importantly this real channel will be time delayed. So this delay will be an integer quantity, and this integer quantity will represent the range to the target. Now this delay, we would like it to be something that is user tunable, so we're going to create a range, a Qt graphical interface range, which creates the delay, and the delay is going to be something between, well, minus n over 2, we're going to see n a bit later, and n over 2. We're going to discover what n is a bit in a second. So now we have a reference channel, which is our reference pattern, and a surveillance channel, which is the backscatter signal received by the antenna, and we wish to perform a cross correlation. Now the GNU Radio Companion provides you the FFT, but you see that the FFT, it outputs here a light blue, which is a stream, and here we have a dark blue, which is a vector. So in between the two, we need to convert the stream to vector as we did when we did the histogram. So we convert the stream to vector over here. Now this quantity here have to match, and the length of the FFT will give us the maximum distance of a target. Indeed, if we have a long time interval between two pulses, then the furthest targets can be far away, but the detection will be slower. So the pulse repetition interval, PRI, gives you the maximum range, and this is this n quantity here, which is the maximum delay that we can separate two targets. So we're going to create a variable with this quantity n, and say we're going to set it to 4096 as a random quantity, but a power of 2 because it's going to be the argument of the FFT here. So we select a FFT length of n, so we need to accumulate n elements, and by default the Fourier transform is 1024, which we set to n, and be careful that the FFT is windowed and the window length must be the same length as the number of elements that we're taking here. The forward or inverse Fourier transform is a matter of convention, whether you're taking the time domain sample x and multiplying by exponential of plus j 2 pi ft or my exponential of minus j 2 pi ft. Depending on the fields, it's one direction or the other. The only thing that matters is the IFFT of the FFT is identity, and because I know the solution in this particular case, we need to start with a reverse FFT. We do the same thing on the surveillance channel, exactly the same story, and then we take the multiply conjugate. So the multiply conjugate is so common that it's given. Again, we rotate using the left arrow, and we can connect these two outputs to the multiply conjugate, which is unhappy because this is working on a scalar and we are creating vectors. So we say multiply conjugate must act on vectors. And from here, we've taken here the reverse FFT in both cases, so now we would like to take the Fourier transform of the result. Instead of taking explicitly the Fourier transform, we can actually take the spectrum analyzer from GNU Radio Companion, and again display the n element that we receive because the Fourier transform is a bijective function. But you see here we have an output as a vector, and the frequency sinks expects a stream, so we finally need to convert the stream to vector, or rather the vector to stream, which is over here. And we rotate using the left arrow, we connect these guys, and the default of the vector is to only take 2 elements, so we must reconfigure to take n elements. And you see that running a correlation is as simple as this. We take the noise source, we have a reference channel, we have a surveillance channel with a variable delay from a user tunable quantity. We're going to take the Fourier transform, multiply conjugate, and analyze the spectrum. We run this. Of course, as usual, we must save this as a Python compatible string, and when we run this, we see here the spectrum, middle button, auto range, so we could have done this in the flowchart from the beginning. And now you see that when we're moving the time delay, here is your correlation, and you see that your correlation peak is indeed moving as we are introducing a delay. So the correlation is working correctly. So this demonstrates how, by wisely using the mathematical properties of here's the autoscale function. So by wisely using the mathematical properties of estimator that you're considering, you can actually compensate for the lack of a signal processing block in GNU Radio Companion, rather than starting to write your own custom block. To conclude this presentation, the beauty of the Fourier transform is that because it's linear, if we have multiple copies of the transmitted signal, so one reference channel but multiple targets at different ranges, then by summing the output and feeding this surveillance channel with multiple copies, we are going to detect all the copies of the targets. And this is what is demonstrated in this flowchart that we're not going to get in details together because it's the same as before, but we have a noise source with a throttle block. This is the reference channel. And now we see that we have 3 delayed copies. These are 3 targets, and each one of these targets is triggered by a delay which is generated by a signal source here. One of them is a triangle, one of them is a square wave, the other one is a cosine. And the sum of these targets will feed the surveillance FFT, and because FFT is a linear process, when we run the multiply conjugate over here, we have a cross correlation which separates all 3 targets. And finally, we take a waterfall in addition to displaying the Fourier transform, which is the spectrum over here. This time we did explicitly the inverse Fourier transform by using the FFT block. And if we run this flowchart, what we're going to see now is all 3 targets being detected. So you see here that we have 3 correlation peaks because we have 3 time delays. We have only one FFT block, but it's linear, so it can separate the 3 contributions. And here are the 3 targets, one delayed according to a sine wave pattern, the other one delayed according to a triangular wave pattern, and the last one delayed according to a square wave pattern consistent with what we just described over here. So these are the three targets that we have delayed by these quantities and which are some here. Thank you for attention. That concludes this series of tutorials.